Swayam Prabha. Digital India. Educated India.
So, today we will finish off with electrostatics, right. Essentially the ion dipole, dipole, that is what we were looking at, right, for the last couple of classes. Now, so this is what we looked at in the last class. So, for example, you have your ion dipole interaction, right, and this varied as 1 by r square with a negative sign for attractive potential. Now, if you have orientational averaging, that means one is moving with respect to the other at different angles, then essentially it becomes 1 by r to the power 4. That is what we have seen last class. Now, the same thing happens in case of a dipole dipole interaction. So, when you have a dipole dipole interaction, then V of r, right, goes as you can see, it is 1 by r cubed, negative sign for attractive potential, but look at the difference. The difference is, for an ion dipole you had the charge q of the ion and the corresponding dipole moment of the dipole. Now, because it is a dipole dipole, that charge is being replaced by the dipole moment. So, essentially that is what it is, and this is now 1 by r cubed, not 1 by r squared, and obviously if it is orientational averaging, you know what happened last time too, right, by 1 by r square was squared to 1 by r 4. So, this the same thing happens here, it goes to 1 by r to the power 6, and this resembles something which we know, right. This is your attractive potential when we talk about dispersion forces, right. So, see this here also you have r to the power 6 dependence, but right now we have not even gone into the dispersion forces as such. Okay. So, you can after that you can have so all these, you know, whatever we have talked up till now, there is no induced dipole, that means everything has either a charge or a permanent dipole in the molecule. There is always something like that. But now let us talk about you know, something inducing a charge separation or a dipole in a molecule which might not be having a permanent dipole to start with. So, what you can see out here is, if you look at the term, V of r is equal to minus alpha mu square, well, do not worry about the rest of the terms. There is a certain term which comes over, which is alpha. Now, what is this alpha? This alpha is the polarizability, right. So, let us quickly discuss about polarizability. So, when we talk about polarizability, what do we actually mean? When we talk about polarizability, what do we actually mean? Can anyone say? I mean, just kind of a very brief definition of polarizability. Distortion of the charge, right. So, well, precisely that is what it is. So, this ensures, or this tells us with what ease, that means how easily can an electron charge cloud be distorted. That is, you can also write this one as, or frame it differently, how easily the internal charge distribution of a molecule will get affected by an applied field E. right. That means you apply a field E, and then this polarizer tells you how easily or to what extent this charge is distorted or how easily it can be distorted, right. So, because it is an induced one, because we are talking about induced dipole, what we can write now is mu induced, this is an induced dipole, right. Mu induced is equal to alpha times E, right, where E is the obviously electric field, where E is the electric field and alpha is our polarizability that we all know. Okay. But there is one thing to it. Look at this. This is a linear term. Linear term in the sense this is a linear expression. That means mu induced is directly proportional to E, right? E. Now, what happens if the applied field E is very large? If the applied field E is very large, then I cannot just represent this mu induced like this. So, what I can rather do is then mu induced becomes alpha E say plus alpha 1 E squared plus alpha 2 E cubed and so on. That means, if electric field is very large, we start considering higher order terms. Now, this is something which you have to keep in mind. We will not be discussing that much in this class, but this is very important. This is very important, especially when people are talking about, I don't know whether you have heard of nonlinear optics, right, where nonlinear means, see, this mu induced is equal to alpha times E, it is a linear equation. The moment you go to this, it becomes a nonlinear equation, right, because of the higher order terms. And nonlinear optics and nonlinear polarizability plays it has a very huge role in present day or present situation, right. So, keeping this in mind, if we go back to what we are looking at in the slide. So, for a dipole induced dipole, this V of r is equal to minus alpha mu squared 3 cos square theta plus 1 over whatever is given, but it varies as again r to the power 6. So, it has a 6 dependence or the distance between the dipole and the molecule. So, the molecule is this, it is represented by a polarizability alpha, and obviously, this one is the center of the molecule, the center of mass, and the mu is the dipole. So, what this one does is the dipole induces another dipole in this molecule, and that is how you get this potential of interaction. So, what you can do now further is, so this is at a specific angle theta, right, but we had done this before, we are not going to have a specific angle, we can have a range of angles. So, in that case, what you can do is you can take the average value of cosine square theta, and the average value of cosine square theta turns out to be 1 by 3, and if you take the average value of cosine square theta to be 1 by 3, now this is what V of r comes finally, right, the simplest expression. So, this is an exercise for you. Can you just on physical principles and based on a very simple equation like mu is equal to alpha E, reason out why it should be having a 1 to the power or 1 by r to the power 6 dependence or r to the power minus 6 dependence, that is for you, that is a homework problem for you, right. Now, look at the last sentence. See, no temperature dependence appears here, as the induced moment is always parallel to the field. Now, please keep this in mind, you are inducing a moment, right. Inducing moment means if I have an ion or a dipole which is inducing, the one which is induced is in response to the one which is a permanent one. So, this one is always correlated or always in response to the first one. That means, if this one, so if this is one dipole where I have a positive and a negative charge, and if it is inducing a dipole, then this one also induces in such a way that the opposite ends are closer, because the potential is always attractive, right, because it is an induced dipole. You cannot have a repulsive interaction in this case, because it is induced. For dipoles which are permanent dipoles, you can always have repulsive interactions because those are not induced, but here you are inducing the dipole, and the dipole induction is such that it is always essentially attractive. Is that clear? Now, let us talk about dispersion forces. So, this is essentially the last topic of electrostatics, and if we just think about dispersion force a little bit. So, what do we really mean by dispersion forces? So, think about this. I have say a molecule which has a certain dipole, right. Now, this is what I was talking about before. If I have a molecule which has a dipole, it will induce on another molecule a certain dipole, right. So, if this is the respective ends, so you will also be having the say oppositely charged ends out here, does not matter what orientation, just keeping it very simple. Now, suppose we have two molecules with no permanent dipole, that means essentially neutral molecules. So, none of these have permanent dipoles. So, say this is molecule A, this is molecule B. So, that means A, think about this, let us look at A first. A also does not have a permanent dipole, and B, obviously we are not talking about B right now, but we know about something referred to as what, instantaneous dipole, right. So, what will happen is, in saying if I am talking about A, depending upon how loose the electron cloud is, fluctuations in electron charge will occur. So, again depending upon how loose the electron cloud is, fluctuations in electron charge will occur. What does it mean? What it means is, suppose I have almost I have a bunch of electrons and I have my nucleus in the center. So, the nucleus obviously always has an attractive potential with electrons, but think about the electrons which are far away from the nucleus, right. They are essentially screened by the inner electrons, right. So, they feel less of the nuclear charge. Now, what this means is, if your molecule is not having a permanent dipole moment, what this means is, because these electrons are far away from the nucleus, these electrons always undergo fluctuations, because see they are not under such a high attractive potential from the nucleus. Now, because of these fluctuations, because the electrons moving in and out, because of fluctuating of this charge cloud, what you can do is, you can give rise to what, instantaneous dipoles, right. So, that means this will give rise to something known as instantaneous dipoles. So, that is for only one molecule now A, right, that is for only one molecule A. Now, to have the dispersion force between the other molecule will also have to respond to this, right. So, that means to keep this dispersion force alive, B has to respond to molecule A's charge fluctuation, molecule A's charge fluctuation, it has to respond. But how can it respond? So, this response of B will also depend upon what? Will also depend on the looseness of the electron cloud of B, right. So, in one case we have an instantaneous dipole we have for A, and to what extent B would react or orient itself to this instantaneous dipole will also depend upon the looseness with which you can deform B's electron charge cloud or electron cloud. hence what you can guess is that my potential energy of interaction V would be proportional to, at least not talking about the distance dependence now, proportional to what? Tell me. One was the looseness of A, the electron cloud of A, that was represented by the polarizability of A. So, I can write alpha A. Then once I have the electron cloud which is already in an instantaneous dipole for A, then I will have the polarizability of B coming in, right. So, it will be having a B term, right. So, this is polarizability of B. And remember, when we talked about this, because this is instantaneous dipole or induced dipole, this is induced dipole. If I have a dipole like this, the other dipole is induced such that it is always attractive, because I am inducing a dipole again, and hence I can straight away write that my potential energy of interaction is attractive. Is it clear? So, we are actually developing the dispersion force, I am sure you know, but it is kind of trying to look at it again from a little different viewpoint. So, keeping it in context of what electrostatics we have been discussing. So, for this, this is direct, this is this is directly evident that it has to depend on the respective polarizabilities, right. So, essentially this depends upon the product of polarizabilities of the two molecules. Now, that is evident, that is clear, and that is very logical. But what about the distance dependence? Now, this distance dependence, it's the derivation of this is a little bit involved, but people have derived it for us, for you, for me, applying principles of quantum mechanics. It can be done. And so, what will happen is, if we go back to the slides, so here V of r is equal to minus 3 by 2 h nu 1 nu 2, you see, by over nu 1 plus nu 2. Then look at this term, we have alpha 1 alpha 2, which is essentially like alpha A and alpha B, right, that is what we have. And then you see the distance dependence, it is r to the power 6, right. This is something we had also noticed for what? Remember dipole interactions, right, when they were orientationally averaged, but here this is induced dipole, but remember it is still dipole, right, whether it is induced or not, it does not matter. That was a dipole, this is also dipole, the only factor is it is induced dipole, and the difference is in those cases instead of polarizabilities what did we have? And do not worry about this nu 1 and nu 2 right now. Instead of polarizabilities we had the respective dipole moments, but here we cannot have a dipole moment, instead that dipole moment is being replaced by polarizabilities alpha 1 alpha 2. Okay. So, what are nu 1 and nu 2? Not that you have to worry about this too much, but it says that these are the frequencies of the first allowed electronic transitions of the molecules, right. And an alternate expression for this V of r is given at the bottom, where V of r is equal to minus 3 by 2. Now that nu 1 by nu 2 or nu 1 nu 2 has been replaced by the respective ionization energies I 1 I 2. So, that means I 1 is the ionization energy of say molecule A, right, or molecule 1, I 2 is the respective ionization energy of molecule 2. Okay. So, anyway, the derivation of this is involved, but and we will not be going through that this class. Okay. So, this was about the dispersion forces, and because these are induced dispersion forces, so we can write induced dipole interactions. Induced dipole interactions, or you can even write instantaneous induced dipole interactions, it does not matter, but at least the message is out there. So, these are what your dispersion forces, these are also referred to as something known as your London forces, right, and people call this interchangeably as Van der Waals forces, right. So, all these things already. Okay. So, what we have done in electrostatics is that we have started with again the Coulombic charge, right, Then what did we do? We went for a charge and a dipole, then we went for dipole, but all these had permanent charges. Then we took into consideration orientational averaging, because obviously they are not going to be constrained, thermal motion would always move them around. After that, we came to induced dipole interactions and saw that this is dependent upon essentially the polarizability of the molecule. So, you think about this, starting from the charge to this dipole, or this induced dipole, or this polarizability, you have typically covered almost every aspect of this electrostatic interaction, except possibly one more thing, which is hydrogen bonding, which we have not yet talked about, but that is a separate topic we will deal with later. Now, let us look at some comparisons. The question that comes to your mind is, sure, I have these different dependencies, right, for this different interactions, how do the energies compare? So, look at this. So, this is a comparison of different interactions at a set distance of 5 angstroms, we have to keep the distance fixed. Now, so say you are given a certain dipole moment mu, say for ionic, so V of r is this, okay. For ion dipole it is 4, dipole 0.5, and dipole induced dipole it is 0.012, and it makes sense, right. As we are going down, not only what happens is that your interaction is decreasing, but you see the distance dependence. The distance dependence, it is 1 by r was literally long range. Remember, we had two terms, long range and short range. 1 by r is long range, and then you come to 1 by r squared, then 1 by r cubed. Beyond 1 by r cubed, it essentially becomes short range, right. So, this is how you distinguish between or differentiate between your long range and short range interactions, and that is how the energies also fall in place, right. Okay. So, having looked at this, another question comes to our mind, and I will tell you what the question is. The question is, okay, we are talking about different potentials V of r, right, we are talking about these potentials V of r. Now, if I am talking about these potentials V of r, then what is a form of a potential? That means, what are some empirical potentials used? Some empirical potentials used. Now, these but we will just again go through it. So, let us look at the first one and the most simplest one, the simplest one. So, this is referred to as a hard sphere potential. This is referred to as a hard sphere potential. Now, what do we mean by hard sphere potential? Say, suppose we draw a potential energy diagram. Say this, I have V of r, and this line is arbitrarily taken as 0 potential energy of interaction. So, now, let me draw another line here. Okay. So, this is your r, and this is distance is known as sigma. So, what it means is, so look at this, what it means is, if I am going to, so this is my V of r and this is r, right, and if I am going to write V of r, what I can write is V of r is equal to infinity if r is less than sigma, right, and V of r is equal to 0 if r is greater than equal to sigma or greater than sigma. And what is sigma? I will tell you what sigma is. But again, look at this plot. We have r, which is the distance, right, between the interacting dipoles or whatever, the interacting species. This is a potential, how it looks like. You can see from here, it just, there is no curve or anything, it just takes off and goes to infinity. This is something which you have come across in quantum mechanics when you are doing particle in a 1D box. Remember, if V is equal to infinity outside the walls, and hence you could not go there. And the same thing is happening here. That means, if this guy is coming here, then V is infinite. Now, what is sigma? Sigma is the diameter of the respective interacting spheres. It is the diameter of the respective interacting spheres, right. So, that means if I have two spheres like this is referred to as hard spheres, right. So, that means these are two spheres and I can take this distance to be sigma in touch with each other. Again, what is the significance of hard spheres? Can someone tell me? Hard spheres is, you look at these, when these two spheres are colliding with each other, if they are not hard, then what might happen is this one might induce a deformation in this one, and hence in that case your distance is going to change, right. But if it is a hard sphere, what does it mean? Hard sphere means these two collide with each other and then elastically bounce off at this distance sigma. That is what you mean by hard sphere. Hard sphere means you just cannot squeeze them further. The moment they are in contact and they come, bounce off elastically and then go away, right. And hence this sigma refers to this. That means because the potential is very high at r less than sigma, they can never encroach that sigma length. That is why the potential is shot up to infinity. Clear? So, there is a hard sphere potential, but see the drawbacks of this hard sphere potential. Drawbacks, well, it is too simple. It is too simple. Obviously, for this the advantage is, it is an advantage for mathematical calculations. And number 2 is, think about this guys, when we talked about this empirical potentials used, see your potential is not only repulsive, right, it also has to have some what, attractive potential, otherwise they will never come together. Hence what we can say is no attractive potential is present. No attractive potential is present. That is the other drawback of this. Your one is obviously too simple. It is an advantage in one sense because you can easily employ mathematical calculations or mathematical treatment with it or to it, and number 2 is these molecules will never face any forces of attraction between each other. Now, that is definitely a drawback. What is the next one? The next one is something referred to as a square well potential. Now, this is also a term, square well potential, which you know from quantum mechanics. When you remember, you did potentials of finite width V naught instead of V is equal to infinity or V is equal to V naught, and then you talked about tunneling, right. So, it is very similar here. You see, try to think about the parity here. So, if I draw the potential energy curve like this, the square well means I will be having a square well something like this. So, let us draw it here. Okay. So, this is again V of r, this is 0, right, this is your r, this is sigma 1, okay, and this is sigma 2. Okay. The depth is epsilon. So, epsilon is the well depth. So, now look at the difference. When we are talking about the hard sphere potential, this term was not there. The only term we had was on the positive side, that means V of r was repulsive, right. Now, we have brought in a attractive term. Because of the attractive term, you see this one is going down, that means there is a negative, it is a negative potential, right. But then the negative potential is just like a square well between this region, it is fine, it is negative. Then the moment your r is greater than sigma 2, what happens? V of r goes to 0. So, here again the drawback is obviously here it rises to potential rises to infinity very fast, and here also it drops to 0 very fast. Okay. The first case it was rising to infinity very fast, no attractive potential. In this case you have an attractive potential, you have a repulsive potential, but both of these are very steep, both of these are very steep. So, here I can say this is the simplest form having both attractive and repulsive potentials. This is the simplest form, right. So, here what we can write is V of r would be infinity. Now, what should the limit be now? R is less than sigma 1, right. Now, V of r would be 0 for, what should I say now, r greater than sigma 2, and then I can also write, let me write it here, V of r is equal to my well depth epsilon, which is my attractive potential energy, if what, r sigma 2 sigma 1. So, only within sigma 1 and sigma 2 do I have, well it is essentially sigma 2 minus sigma 1 essentially you can say, because it is just this guy, right. It is only this part where it is attractive. Okay. So, that is why it says it is greater than sigma 1, but less than sigma 2, it is essentially sigma 2 minus sigma 1. Okay. So, this is one form again, but as I said it is not that realistic, it is a simplistic form, but it is not realistic at all. So, that is why the one people use and the most common one is, can someone say what it is? Is referred to as the Lennard-Jones LJ potential. And how does it go? This you guys have seen many times. It goes something like this. I have V of r, right. This well depth again is epsilon, right, and this one from here to here, this one is sigma, okay. And obviously this is r, and this Lennard-Jones potential V of r is equal to 4 epsilon, right, then sigma by r to the power 12, sorry, well r minus sigma this, or I can write it a little better, sigma by r 12 minus sigma by r plus 6. So, this is the Lennard-Jones potential. What it does is, this is a repulsive term, this is the attractive term, okay, repulsive, attractive. This is your well depth as it has been defined here. Now, what is sigma? Sigma is that distance, you see this distance sigma, where V of r is equal to 0. So, look at this, this is my 0 line, right, this is my 0 line, see this is my 0 line, this line is my 0 line, V of r is equal to 0, my x axis essentially. So, when this V of r crosses this line, what happens? It goes to 0, and that is the distance which is essentially your sigma, okay, that is how sigma is defined. So, here sigma is that one where V of r is equal to 0. Now, do not consider the fact where, I mean, if you come on this side where r is very high, your V of r is also 0, right, because there is no interaction. but do not consider that point. I mean, it is no use. The way it is defined is, if you come here, then V of r is equal to 0. This is the point where V of r is equal to 0. Okay. See, immediately one thing you can realize, this r to the power 6 dependence we have seen already, right, from induced dipole, 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 dipole and all those things. This one is a repulsive term, it can be derived, but this is one of the ways that people have found very convenient to represent a repulsive term. The good point is that unlike the previous ones, whether it is this one or the hard sphere potential, where if you r would be less than sigma, it would immediately go to infinity. This one does not, it goes to infinity, but with the dependence of r to the power 12 or 1 by r to the power 12, and this is the one which is most commonly used nowadays in many different forms, and I will tell you what form I am talking about. Okay. So, from here, this is a homework problem. What you should be able to figure out, this is a homework problem. At what r for a Lennard-Jones potential is V of r minimum? At what r for a LJ potential is V of r minimum? That means your potential is minimum, right. So, essentially the hint is you do dV of d of r is equal to 0 and then express r in terms of sigma. Okay. That is what you will have to do. Okay. So, that essentially brings us to a discussion about electrostatics, but there was a question that was asked, how do we actually do it in molecules? So, if you go to the slides, so let me go to the slides now. Now, there is something known as molecular mechanics. What is molecular mechanics? So, for example, think about the situation. I have given you a protein, because this is biophysical chemistry, let us talk about a protein. In proteins, you will be having different amino acids, you will be having different charge-charge interactions, different dipole-dipole interactions, right. Whatever we have looked at up till now is essentially between two species, but there will be many. And this potential of interaction, what are the different things you should consider, and how do you consider, how do you actually calculate it? So, this is done by something known as molecular mechanics. So, as it says, molecular mechanics describes the potential energy of a molecule in terms of a set of potential energy equations. Now, these potential energy equations we have already seen, right, V of r for many different systems, this you have already seen, not all though, but at least you have looked at it from the electrostatic point of view, that resemble classical mechanics is physics. So, that is why it is called molecular mechanics. So, see, quantum mechanics is all about molecules, right, and classical mechanics has all these Newton's laws of motion and all these things. When you merge these two, essentially you get molecular mechanics. That means you are applying classical mechanics to a molecular description. That is what molecular mechanics is all about, right. So, the next is, if people would be working on molecular mechanics, they would be using something known as force fields. Now, remember, all this potential energy of interactions is essentially forces of interaction, right. So, the potential energy equations, to calculate the energy that define the different interactions in a molecule and the parameters, whichever you can vary to define these interactions, together constitute the force field. That means you are creating a field in which you are taking into account all possible interactions giving rise to certain potential energy. Is it clear what a force field is? So, force field means you are talking about, you take a molecule and you are talking about all possible interaction energies, potential I am talking about in a molecule, right, and the field tells you that in this field I better make sure that I take into account all possible sets of potential energy interactions, right. That is what a field is. The field involves everything, it is a field, that is, it has all the typical interactions that can ever occur or supposed to occur in a given molecule. Now, it will become more clear once we go to the next slide. So, look at this. What are the different interactions that can happen? Well, this is very simple, right. This is a typical, say, a peptide bond or whatever you are looking at. See, you can have one is a bond stretching, and if you remember harmonic oscillator, what was the potential? It was half kx squared, wasn't it? So, but that is the potential energy of interaction. It is not obviously electrostatic in that sense, but it is a potential energy of interaction, isn't it? Then we can have bending motion, right, like we have stretching, symmetric, antisymmetric, we can also have bending, that is also potential energy of interaction. Okay. Then we can have torsion, that means you are moving it with respect to a bond, you are doing a torsion application, that is also a potential energy of interaction. And last but not the least, you can also have non-bonded interactions. This is the interactions we have talked about in at length in electrostatics, especially the dispersion forces, van der Waals and all these things, even the Lennard-Jones potential. Now, what is missing from here? Obviously, what you can point out is a hydrogen bond situation, right. Hydrogen bonds are typically not very easy to model, but people have come up with certain components in force field which can take into account the hydrogen bonding situation. But let us not worry about the specifics. The idea is that if you would want to calculate the potential energy of interaction or the energy of interaction in terms of force field for a given molecule, these are all the different terms you have to look at. You see, the first one, what is it? The first one is, so this is V of r, right. The first one is essentially a stretching, right, half kx squared, right. Now, this is bond stretching we are talking about. In the next slide I will tell you what L0 means. The next one is the same for bending. If you can have a stretch, you can have a bond bend, the same thing will happen, a different force constant though. Next you have a torsion. The torsion is given by this equation. This we have not talked about at length, we will just keep it at that. But look at the last term. The last term is something we are familiar with by now, right. The first one is what? Your Lennard-Jones potential, and the last one is what? Your Coulombic, right. That is what you know. Obviously, we will be having many iron dipole and all those things, but this typically is a very broad thing, it covers almost everything except the hydrogen bond we have talked about. Now, just looking at this individually real quick, if you are talking about the first term, which is the bond stretching, right, this, you know, this force constant is typically the curvature of your potential energy. The force constant k is your, if you remember, it is d2v over dx squared, let us not go there now, it is the curvature of your potential energy surface. This k you can get easily from vibrational spectra, and this you know. What is L0? L0 is the equilibrium distance you obtain from X-ray crystallography. That means, if you are going to take a protein molecule and if you are going to find out this force field or potential energy of interaction, you better have the crystallographic coordinates or at least the bond length of the respective bonds I am looking at. This you can only get if you have the respective crystal structure of the protein solved. That is why if you see people working with molecular mechanics, most of the times or almost all of the time they would be working on proteins which have crystal structures already deposited in the protein data bank, because they have the coordinates, and if people have coordinates they immediately have what? The bond lengths, bond angles and everything, the lattice parameters essentially, right. So, this is now you know what L0 stands for, and L minus L0 is what? It is essentially a force of extension, or rather length of extension or length of compression, whichever you are looking at. Okay. Now, this is just for information. Now, there is angle bending, the same thing again, from crystal structure you will be having theta and all those things. This is the torsion term. Now, the torsion term as it goes, you look at n, n is a multiplicity, multiplicity essentially is the periodicity of your vibration or the periodicity of this torsion. Okay. So, n is equal to 1, 2, 3, 4, it can go on like that. Omega is the torsion angle, the angle around which we are doing this torsion application, and gamma is referred to as the phase angle. And you know, these are different, I mean, this is for red is for Vn is equal to 2, n is equal to 3, where periodicity is 3, and this one is for n is equal to 2, gamma is equal to 180. So, these are different things people look at, and obviously the last term which we had, if you remember, the last term was something we just looked at some length. So, this is again the importance of this is people when doing or looking at force fields would typically include these, and so these are the basic minimum or the bare minimum we have to include in the force field. Now, if you start talking about very specific interactions like hydrogen bonding or some other types of interactions, you start refining this potential by adding extra terms or adding extra parameters. That is what you do. But this, guys, in a nutshell, is what people do when they do molecular mechanics force field calculations, right. And you can understand, depending upon the size of a protein, you will be having so many atoms. You can understand, however, how many atoms they will have to do it, right. And computation, it becomes very time consuming, because if you are doing it through a computer, obviously you have to do it through a computer, you cannot do it by hand. The computer has to look at each and every such interaction for each and every atom in a protein, and when the computer tries to do these calculations, it obviously is going to involve time. This is also another reason why it involves time, but we do not go there, but this is essentially what a computer does, or how a program is built in by people. There are force field programs. I do not know whether you have heard of programs like, I will tell this to you maybe in next class, like AMBER. There is something known as AMBER force field, there is something known as a CHARM force field. So yeah, so the CHARM is so from Harvard, so it is Harvard molecular mechanics, that is why CHARMM, C is obviously chemistry, right. So you know, it is actually, if you kind of spend some time with these force fields, you will understand that it is not that something you do not know. You go into the force fields, you look at these things, all these things you know. Know means at least you can vision, you understand what it is. It is just a mere application of these, mere taking these things and putting them together. That is what it is all about. Nothing is new to you, you know, that is what the point is. Okay. So, you know, that is what about, that is pretty much what I need to tell you about electrostatics, and I just thought I would make this connection so that you understand how electrostatics is being used by people to look at different proteins. The next topic, I will just touch it briefly and we will start the next day, is hydrophobic effect. Now, hydrophobic effect is of huge importance. Okay. So, this effect plays a central role in chemistry and biology. It is very important, and we will try to understand hydrophobic effect from the very basics. What does hydrophobic effect start from? It essentially starts from the fact, where does it start from, that non-polar molecules tend not to dissolve in water. Instead, these molecules tend to self associate. Instead, these molecules tend to self associate. This you all know, right? Now, think about this in terms of the perspective of a protein folding. Remember, we talked about some length, you know, at some length about nascent proteins and peptides, and we said that the tunnel, ribosomal tunnel, does not give it enough space for the full protein to fold. So, depending upon what protein you have, a part of it has to fold outside the tunnel, and when the protein is folding, you are essentially what you are having is you are taking your hydrophobic amino acids and putting them in the interior. The simple reason being that hydrophobic amino acids do not like water, right. But how would you model this? You cannot just take a protein and try to model hydrophobic effect, because the protein has so many amino acids, right. Which one would you take, which one would you not take? So, then this is where we will start from tomorrow, but just remember this. There is a scientist called Walter Kossmann. Walter Kossmann in 1958-59, he came up with this theory of hydrophobic effect, and he said that if I have to model this burial of a hydrophobic or non-polar amino acid side chain when it goes from, say, when it goes into water, it is going inside the interior. How can I do it best? What I can do is I look at the amino acid and I take a model compound. I take a model compound and I look at that model compound's energetics when it is getting dissolved in water. If I can do that, and if I can compare this one and that one, then possibly I should be having an idea of the energetics involved in this hydrophobicity. That means when a protein is getting buried, or when a protein's interior has all these buried hydrophobic residues. So, essentially you model a protein's interior, or you model this transfer of hydrophobic amino acids from water to the protein interior by doing just the reverse, or essentially if you look at the other direction, that means if you are opening a protein, you are taking the hydrophobic amino acids and exposing them to water. What you can now do is try to model that by taking an organic molecule, put it in an organic liquid, you take it out and now put it in water. That is the same thing you are doing for a protein, and then you compare the energetics and try to model that. So, that is what Kossmann, that was a brilliant idea that Kossmann came up with, okay? And that is what hydrophobicity is all about. But I hope I can stress upon you the importance of hydrophobicity, and you will see how hydrophobicity can be developed. It is actually quite nice, okay? And